Hello guys, today I will be doing same problem, example 2. Uh, but this time we're going to use the allowable stress design method to solve the problem. So here, there's an additional equation formula I added to the lecture. And this formula actually are the ASD equivalent of the formula I presented in the recent lecture. So for this first formula you can see here, this is actually the formula for inelastic buckling column or column buckling. Okay, or what you call the short column buckling. And this formula here is for the elastic Euler uh, column buckling. Is for long column. Okay, so for our general criteria on the strength limit state, we know that the resistance is always greater to or equal to the load or load effects. And for ASD, the comparison for your resistance, which is actually your F CR, or rather FA, is equal to F, the resistance, all over uh, the factor of safety omega. Okay, so this is the one we're going to derive. For this, we're in this value in the parentheses with the Fy. There's actually the SSRC uh, parabola that serves as basis uh, for your curve. No? So this is a perfect parabola, which is actually equivalent to a simple 1 minus lambda sub c squared over 4. Okay. So of course, so your lambda here, your omega here is actually the factor of safety, which is okay uh, given here below using another formula equivalent to a constant and a ratio of the slenderness to that of the limit, and so this is the one that you plug into your omega. Okay, for the elastic Euler long column, so the formula is simpler, and we take note that your FA here can actually be written as your simple Euler formula all over a factor of safety omega. No? So this is simply equivalent to pi squared E all over KL over R squared divided by a factor of safety equivalent to 23 over 12. So here your omega is actually this 23 over 12 or 12 over 23, which is written here in as a coefficient of the Euler buckling formula. So we simply take note that upon uh, uh, determining whether or not your column uh, behaves in terms of inelastic buckling or elastic buckling, The next thing to do is just to plug in the value of KL over R and C sub C in this equation. May I remind you that the value of C sub C here is simply the limit corresponding to your lambda sub C, which is square root of 2. Okay, so this is your column strength curve, which has a shape of a half bell curve depth. So we have here your limit, so which is lambda sub C in LRFD and C sub C in ASD. So take note that C sub C is just the limit of KL over R which can be derived using the formula square root of 2 pi square E over Fy. Okay, so this square root of 2 here is actually the value the value of your lambda sub C in LRFT. So let's plug it here in this equation. This problem has been solved using tables. So let us try to check whether we can get the answer. So if your prevailing governing KL over R is in the x direction, we have here now a 54.55 value. So we just make use of the formula. Okay, so FA. So this is KL over R is less than CC. Okay, so what's your CC? CC squared of 2 pi squared E over Fy, which is actually equivalent to, I think, so your Fy here is given to be an A992 still, so this is equivalent to 50 KSI. Okay, so you take the square root of that, you get 107 or 106.99. So this is 107. So this is now 54.55 less than 107. Therefore, this is inelastic buckling. So you just use the formula FA is equal to 1 minus 54.55 squared divided by 2 times 107 squared times 50 all over your factor of safety, which is 5/3 plus 3/8 of 54.55 divided by 107, and then plus, or sorry, it's minus 54.55 cubed all over 8 times 107 cubed quarts. Okay, so let's separate the numerator from the denominator. So the numerator is 43.5. So let's multiply it by a factor of safety of so this is times -1. Okay, we add it to 54.55 plus 107 times 3 over 8. Okay, then add 5 over 3. So we get 1.84 here. So the value for your FA is 43.5 plus 1. It's 23.64. Okay, so there's a slight, because this is only through the use of the table, uh, there's a slight discrepancy. So this is 24.09 KSI here. So this is the comparison, and therefore your nominal capacity divided by lambda sub c will simply be equivalent to your FCR over lambda sub c, or simply FA AG. Okay, so this is now 23.64 times AG is given in the problem to be equivalent to it's a W12 by 58. So let's take a look at the table. Okay, so I think I have here my table, the excerpt of my table 12 by 58. So the area is 17 inch square. Okay, so the area is 17, so you just multiply this by 17 or 23.64 times 17. So this is in KSI and inch square. You get your answer in kips. So you have 40.19 kips. So compared to the answer using tables, which is so this is 401, sorry, 0.9. Okay, so stand corrected. So this is 401.9 kips. Okay, so your answer there is 410 kips. Of course, the use of the equation is more accurate than using tables because charts and tables have some difficulty in interpolating, no, the values on the charts and the table. So that's it. Thank you very much for listening.